Good morning, everyone. Today, I would like to present to you our report of Group 1 about properties of polar and non-polar molecules. Objectives. At the end of this lesson, the learners will be able to differentiate polar and non-polar molecules, relate the polarity of molecules to certain substances, and recognize the importance of Lewis dot structure and molecular geometry in identifying polar and non-polar molecules. Before we proceed to our discussion, let us answer the following question in the screen. Number 1. It is composed of only two atoms of some or different chemical elements. The answer is diatomic molecule. Number 2. What is defined as two or more atoms of the same or different element that are bound together? It could be homonuclear, consist of atoms of one chemical element, or heteronuclear, a chemical compound composed of more than one element. The answer is molecule. Number 3. It is a way of expressing information about the proportion of atoms that constitute a particular chemical compound or molecule. The answer is molecule. Number 4. These are diagrams that show the bonding between atoms of a molecule and the ion pairs of electrons that may exist in the molecule. The answer is Lewis structure. Number 5. It is a model used in chemistry to predict the geometry of individual molecules from the number of electrons pairs surrounding their central atoms. The answer is VSEPR theory. Number 6. It is a measure of the ability of an atom in a molecule to draw bonding electrons to itself. The answer is electronegativity. Number 7. The electrons involved in the bond between two atoms are shared. The answer is covalent bonding. Number 8. A kind of bond wherein one or more atoms lose their valence electrons and another one or more gain these some electrons to achieve noble gas electron configuration. The answer is ionic bonding. Now, after we answer all the questions, let's start our discussion. It is very important that before we begin with a discussion on polar and non-polar molecules, we must have a strong foundation on the concept of electronegativity of elements. Below is a periodic table of elements with corresponding electronegativity values of each of the elements. What is electronegativity and why is it important in the discussion of molecular polarity? Let's dig in. As you can see below, there is an illustration about periodic table of elements with their corresponding electronegativity. Electronegativity is the property of an atom which increases with its tendency to attract the electrons of a bond. If two bonded atoms have the same electronegativity values as each other, they share electrons equally in a covalent bond. Usually, the electrons in a chemical bond are more attracted to one atom, the more electronegatively one, than to another. This results in a polar covalent bond. If the electronegativity values are very different, the electrons are not shared at all. One atom essentially takes the bond electrons from the another atom, forming an ionic bond, which means that electronegativity is the property of an atom which increases with its tendency to attract the electrons of a bond. So, if two bonded atoms have some electronegativity values as each other, it is called covalent bond. And if the electronegativity values are very different, the electrons are not shared at all. One atom essentially takes the bond electrons from the another atom that may cause forming an ionic bond. Next is polarity. The properties of the molecule are related to their polarity. To understand the relationship, you must be able to describe the force of attraction between the molecules. Below you can see an illustration of force of attraction between the molecules. Polar molecules have partially positive and negative ends. When two polar molecules are near each other, the negative end of one molecule is attracted to the positive end of the another. The separation of charges results in a strong force of attraction between the molecules. On the other hand, nonpolar molecules do not have positive or negative ends. Between two neighboring nonpolar molecules, the attraction is very minimal. So we can say that polar molecules have partially positive and negative ends. But when two polar molecules are near each other, the negative end of one molecule is attracted to the positive end of another. Well, on the other hand, nonpolar molecules do not have positive or negative ends between two neighboring nonpolar molecules. Also, their attraction is very minimal. Keep it in mind. How do you relate the strength of attraction between molecules to their observable properties? To answer this question, let us continue our discussion. Solubility. Do you remember the rule of thumb? Like dissolves like. In your previous chemistry lessons, this rule is applied on the concept of solubility of molecules. Solubility refers to the ability of a solute to dissolve in a certain amount of solvent. Polar solutes dissolves in polar solvents. For example, sucrose is soluble in water because both are polar molecules. On the other hand, nonpolar solutes dissolve in nonpolar solvents. For example, hexane and benzene are nonpolar molecules because they only contain nonpolar CH bonds. The combination of these molecules forms a solution. Water and vinegar mix because they are both polar substances while gasoline and oil are non-polar substances. At the upper part, you can see the illustration of water used as a solvent. Melting point. Melting point is the temperature at which a solid turns into liquid. Heat is needed to break the forces of attraction between the molecules because the polar molecules have relatively stronger forces of attraction compared to nonpolar ones. Greater amount of heat must be applied to break these forces. Therefore, in general, polar molecules have higher melting points than nonpolar molecules. Take note that in general, polar molecules have higher melting points than nonpolar molecules. And a very good example for this is the illustration below. An example of hydrogen fluoride is polar while fluorine is nonpolar. As you can see in the illustration below, Hydrogen fluoride or HF has a higher melting point rather than the fluorine F2. Boiling point. Boiling point is the temperature at which a liquid turns into gas. Similar to melting point, greater amount of heat is needed to break the forces of attraction of polar molecules compared to non-polar ones. Generally, polar molecules have higher boiling points than non-polar molecules. Take note that polar molecules have higher boiling points than non-polar molecules. For example, methanol is a polar molecule while methane is non-polar. The boiling point of CH3OH is higher than that of CH4. Now, study the illustration below to compare a polar and a non-polar molecule. Water molecules are polar. The partially negative end of one molecule is attracted to the partially positive end of another molecule, while carbon dioxide molecules are non-polar. There is a minimal force of attraction between the molecules. As you can see in the illustration of carbon dioxide molecules that are non-polar, the molecules has a minimal force of attraction between the molecules, so there is a distance between them, as you can see. So based on the interaction of molecules, water is expected to have higher melting and boiling points than carbon dioxide. Below are the actual melting and boiling points of the compounds. As you can see the table below, the compound is composed of water and carbon dioxide, and as you can see the differences between their melting point and their boiling point. Water have a melting point of 0 Celsius and the boiling point is 100 Celsius. Carbon dioxide, on the other hand, have a melting point of negative 56.6 Celsius and boiling point of negative 78.5 Celsius. In the O2 molecule, both atoms have the same electronegativity. The electrons in the covalent bond are shared equally between the two oxygen atoms. Most and least electronegativity elements. The most electronegative element on the periodic table is fluorine, have an 3.98. The least electronegative element is cesium, 0.79. The opposite of electronegativity is electropositivity. You could simply say cesium is the most electropositive element. Note that older texts list both francium and cesium as least electronegative at 0.7. But the value of cesium was experimentally revised to the 0.79 value. There is no experimental data for francium, but its ionization energy is higher than that of cesium. So it is expected that francium is slightly more electronegative. You must take note of that. Electronegativity as a periodic table trend. Like electron affinity, atomic ionic radius, and ionization energy, electronegativity shows a definite trend on the periodic table. Electronegativity generally increases moving from left to the right across a period. The noble gases tend to be exceptions to his trend. Electronegativity generally decreases moving down a periodic table group. This correlates with an increased distance between the nucleus and the valence electron. This illustration is another concept to learn in the Lewis structure. Lewis diagrams made easy. There is a question. How many valence electrons does chlorine have? In Lewis diagram, that's represented valence electrons. So if you see in the Lewis diagrams that there are that means dots stands for valence electrons. Remember that in covalent bonding, atoms share valence electrons in order to get a full octet for duet for H. And shared electrons are counted as owned by both atoms. Also take note that one line is equal to single bond or equal to 2 electrons. Two lines equal double bond is equal to 4 electrons. Three lines equal triple bond equal 6 electrons. Two dots are called a lone pair of electrons. In addition, you must have a take note of these steps for drawing a Lewis diagram because it is very useful for us and for you for your knowledge. For you to understand the steps for drawing a Lewis diagram, let me explain you the Lewis diagram of a water that H2O stands for. Number 1, count all the valence electrons. So as you can see in the table of element, H have a 1 valence electron in the top of it. As you can see in the table of elements, H have a 1 valence electrons times 2 equals 2. 0 had a 6 valence electrons times 1 equals 6. 2 plus 6 equals 8. So now we have a total of 8 valence electrons. Step 2. Determine the central atom, the element there is one of. So our central atom is oxygen. Now we will write the oxygen at the center and the hydrogen in the side of it because there is H2. 2 stands for 2 hydrogen. After that, we need to draw single bonds to the central atom. So as you can see in the illustration, the oxygen and 2 hydrogen have a single bond in their illustration. After all these steps that we've followed, now we have the Lewis diagram of H2O or water. In additional, that numbers that you've seen in the table of elements 1, 2, 3, 4, 5 to 8 stands for valence electrons. Molecular polarity. Molecules as well as bands can have polarity. A molecule as a whole is polar if electrons are attracted to one end of a molecule than to the another end. Such a molecule has a slightly negative end and a slightly positive end. And we say it has a dipole or is a polar molecule. The slightly negative end of a polar molecule is denoted by a delta minus and a slightly positive end by a delta plus. Consider the HCl molecule with its one polar band with only one polar band present. It should be obvious that the chlorine end of this molecule must be slightly negative and the hydrogen slightly positive, resulting in a polar molecule. You can see below the illustration of CHL molecule with slightly negative and positive ends, as H hydrogen is the slightly positive and Cl chlorine stands for slightly negative. Now consider the linear molecule beryllium hydride BeH2. It has two equal magnitude polar bands, but the dipoles are oriented in opposite direction and those cancel one another, making the molecule nonpolar overall. As you can see, this is the illustration of the linear molecule beryllium hydride. As yet another example, consider the water molecule. If it were linear, then it would be nonpolar. The dipoles of two bonds would cancel because the center point of the positive charges of the bonds would be in exactly the same place as the center of the negative charges, right in the middle of the molecule. Remember that no center of charge separation means no molecular dipole. At the upper part, you can see the illustration of dipole moment of water molecule. The water molecule is actually angular, however, so the bond polarities reinforce one another instead of canceling. The center of positive charge is midway between two hydrogen atoms, as you can see in the illustration. The center of negative charge is at the oxygen atom. Thus, the center of charge are separated and the water molecules are polar. Because of that, we can say that water molecules are polar. In order for us to know whether or not a molecule containing polar bands has a molecular dipole, is apolar, we must know first the molecule's shape or geometry. A useful theory is that a valence shell electron pair repulsion, or VSEPR, pronounced as VSEPR. It states that the shape of many molecules is determined largely by the efforts of the valence shell electrons to stay out of each other's way to the greatest extent possible. Below is a table showing the predicted molecular shapes using VSEPR. As you can see, this is the molecular geometry chart. Molecular geometry chart composed of 5 columns. The first column consists of number of electrons groups. Second one is number of lone pairs. Third, electron pair arrangement. Fourth, molecular geometry. And 5, approximate bond angles. So as we can see, electrons pair have different arrangement. For example, is a linear arrangement. Make sure that you have a copy of this table because it is very important to know the molecular geometry of an molecule. Now, in this part, you can see the regions surrounding the central atom, 2, 3, and 4, and their corresponding molecular geometry or shape. Please copy these examples and the polarity of each molecular geometry. Comparison of polar and nonpolar molecules. Polar molecules, when a hydrogen atom is bonded to nitrogen, oxygen, and fluorine, then it is more likely polar. H2O, NH3 is an example of a polar asymmetry, either containing lone pairs or electrons on a central atom or having atoms with different electronegativities bonded. Polar molecules also a molecule in which one end of the molecule is slightly positive while the other end of it is slightly negative. A diatomic molecule that consists of a polar covalent bond such as HF is a polar molecule. While in other hand, nonpolar molecules, when it is made up of one element, diatomic molecules such as N2 and O2 is an example of it. Noble gases such as helium, neon, argon, xenon are considered nonpolar. Also, molecules that contain carbon and hydrogen are more likely nonpolar. Symmetric, meaning all of the sides around the central atom are identically bonded to the same element with no unshared pairs of electrons. Notice that a tetrahedral molecule such as CCl4 is nonpolar. Another nonpolar molecule shown below is boron. Trifluoride is a trigonal planar molecule and all three peripheral atoms are the same. In addition, in polar molecules, the electrons in the bond are nearer to the F atom. This side of molecule takes on a partial negative charge, which is represented by negative delta. The other side of the molecule, the H atom, adopts a partial positive charge which is represented by delta positive. The two electrically charged regions of either end of the molecule are called poles. Similar to the magnet, have a north and a south pole. A molecule with two poles is called a dipole. See figure below. Hydrogen fluoride is a dipole. If the electronegativity difference of atoms is more than 0.5, then it is most likely polar. There is an unequal sharing of electrons in the bond of polar molecules. On the other hand, on nonpolar molecules, if the electronegativity difference of atoms is less than 0.5, then it is most likely nonpolar. There is an equal sharing of electrons in the bond. In summary, or a important reminder that you must put in your head, if the bonds in the molecule are nonpolar, then the molecule can only be nonpolar. 2. A molecule with only one polar band has to be polar. 3. A molecule with more than one polar will be nonpolar if the shape of the molecule causes the polarities of the bonds to cancel. If the bond polarities do not cancel, then it will be a polar molecule. So again, as I have discussed before, here are the steps in identifying polar molecules that you must copy for your own knowledge. Overall, we've done tackle all the lessons of this module, hoping that you have learned anything from it. Thank you for listening and God bless. Thank you.